All right, here we go. This is conditional probability. So there we're talking dependent versus independent events. So when it's dependent, items like something to look for in the problem in particular is items not being replaced. It could be explicitly stated, or it could be that a teacher is selecting one student and wants to select another student from the students that remain. So kind of like they're indicating that the total has decreased. So the first event does affect the second. So that's something you're looking for. And in terms of notation, if you want to signal that to someone, you would say that probability of A and B happening, like the first and the second event, would be probability of the first one times probability of the second event, given that the first one happened. This is indicating your audience that, oh, wait a minute, this one affected this event. They're not going to have the same denominator if you were to look at cards, for instance, right? It's going to be 52, 51. This is how you indicate that. Independent events are where items are being either replaced or the first one just simply doesn't have an effect on the second one. So dice, spinner, coins are usually independent. I can't see a scenario where they change that. I mean, they would have to like remove from a die, right? They would have to remove that number maybe, but that would be a very weird question. So in a sense, probability of A and B happening is just simply taking the probability of A, not caring what happened first and just taking, hey, the probability of B happening, what is that? This is how you would signal that, and both of them would have the same denominator if you're grabbing from the same deck of cards, for example, or if you're spinning a spinner that has like 8 sections, it would be something over 8, right? That wouldn't change. Probability of drawing one card after another without replacement is the classic. So let's say you want to grab a red face and a red card. And remember, one after the other is the key here as well. Sometimes when it's a hand of cards, if they don't tell you one after the other, you want to be using combinations. You do not want to be using this method. Coincidentally, this method works if you're taking two of the same card, let's say you want 2 reds or 2 aces, 2 faces, something like that. This works no matter what. But if it's from the two different, let's say 2 different suits or something like that, and it's not one after the other. I'm just talking when it's not one after the other. If you just grab a hand, and let's say you want 2 faces and 1 ace, like 3 different cards, but you're wondering how many hands of those like that have those 3 cards in them can you make? Use combinations, and I'll show you that in a bit. A black card and a red card. Sorry, let's go back to this one. Red face, there are 6 out of 52, and a red card. You're down to 51 cards for sure. You lost a card because you grabbed one. And since the first one was a red card as well, you're down to 25 red ones now, right? You indicate that. So that's how you would do that. A black card and a red card, it's 26 over 52. And you still have all red cards, but you're down to 51 because 1 card was removed from the total. Okay? Tossing a coin and rolling a die. So rolling a 5 and a 2, let's say. Again, it's 1 over 6 times 1 over 6. It's 1 over 36. You can look at this and see that these events are independent, right? You can tell that it's not decreasing. That's another way of checking. Probability of heads and rolling even. There's 1 over 2 for heads, 3 over 6 for rolling an even, right? 3 out of the 6 are even. Again, you just multiply and then you end up with a quarter. Okay, don't forget about your outcome table, especially when it's sums. Okay, and the other classics, by the way, these here would have been considered independent here. These are independent. dependent. Just by the nature of the question. Okay, you're not removing anything. Even if you removed it and it's being put back, it would still be under the independent category. Next, you've got, I just made one of these. These are one of the classic tree diagram questions where you have dependent events. So there's an 80% chance. If Mr. D drinks coffee, there's an 80% chance that he's happy. If he doesn't drink it, he's only happy 55% of the time. There's a 90% chance that he drinks coffee every day. Okay, so sorry, this one bled over, so I need to expand my long sheets here. So basically, I compare drinking coffee and not drinking coffee. That's kind of what sets everything off. So there's a 90% chance of drinking, therefore 10% of not drinking. Being happy and not happy is different when I drink coffee than when I don't drink coffee, right? These ends are different. So that is kind of like a clear giveaway that this is a dependent situation. You multiply everything out. If you want the probability of Mr. Dirksen not being happy, then you just add all the instances where it's a not, H not, right? So these two, you add that up, and you get 0.225. I am just going to check something here because this is 0.1 times 0.45. That's 0.045 here. My bad, right? And then, so I did get that right here. So you add, and it's 22.5%. Probability of being happy, you add up the ends where Mr. Dirksen is happy, that's 0.775, and no surprise, this should add up to 1, right? Happy, not happy. And the last one is a given situation, right? So how would this translate? Probability that Mr. Dirksen drank his coffee given that he's not happy. So you have both of these and like this, and it's this one that goes down here, not happy, right? So I go get this one from my tree. Having coffee and not happy would be right up here, 0.18. And then probably of not happy, I already figured it out earlier, it's 0.225, and so that's 80% chance, okay, that happens. So this is conditional. And I just wanted to make a specific reference. I had to add that somewhere else about cards. I would say, especially if you're doing a hand. So combinations or fundamental counting principle. So if it's two aces and one face, if you do it this way, again, this is only if it doesn't say one after the other. Okay, if you're doing hands, then if you did it this way, you would get that answer. If you did combinations, like two aces, right? 2 out of 2 choose 2, and that's actually not right. 2 aces there, 4. 4 choose 2. Okay, this would say, if I want 2 aces, I need to consider that there are 4. I just choose any 2, and therefore this number here is going to be 48. Choose 1. Actually, what am I doing here, right? 12 faces, so that's 12 choose 1. So 4 and 12, that's 16. So technically, there are still more cards, right? 36 cards. But I'm going to choose none of them. So I'm just going to focus on, from the 4 aces, I choose 2. From the 12, I choose 1. So 4 choose 2 is 6. 12 choose 1 is 12. And that's 72 over 52 choose 3. It's 22,100. So I'm going to make this a 22,100 here. Sorry about that. I didn't think of it sooner. So this one reduces to 18 out of 5525. So you notice that the answers are different. So this is only if one after another, without replacement. Go for it, use this, it works. Okay. But if it's saying, if this is just hands, and the hand is supposed to have two aces and one face, and it doesn't specify that it's one after the other, then you have to do it this way. This would be a probability of that happening, right? So they are different, so just look for the keywords there. And that's all I wanted to say for this part.